So I take it we're ready to go. This is going to be the second lecture in the six-part series for those that missed last week. We went through basically the physical and chemical structure of what we call the atmosphere and the various interfaces that relate to the atmosphere, the ocean interface, the cryosphere, the different parts of the atmosphere, why they're important, and the fact that we live in the troposphere. So we covered all that basic weather and climate and the relationships to it. And with the chemistry, we talked about the greenhouse gases, and the principal ones are carbon dioxide, methane, and water vapor. And then there's some oxides, nitrous oxides, that kind of thing that go into it. And then we basically started looking at the major problems that we have with the addition of various gases like methane and carbon dioxide into the atmosphere and the issues that it presents. So we put that all into context. Like, what are we talking about here is basically what last week was about. This week, we're going to be looking at paleohistory. And paleohistory basically covers the inception of the Earth 4.54 billion years ago to the current time of the Earth. And before I get into today's lecture, I did want to announce that it's been pointed out to me that we've had some very good news on the climate mitigation front from the federal government. I have a little news clipping here that says that Dow has landed some ocean research money to the tune of $154 million to study the effects of climate change on the oceans through a consortium with a number of other universities. And this is part of a $1.4 billion infusion of cash into the general studies of climate change by the federal government. And they're funding 11 different large-scale projects. So this will go into next week's lecture. Next week's lecture will be looking at basically the large input of NGOs, industries, government on all levels, federal, provincial, and municipal, in terms of coming to addressing the climate crisis. And when we talk about addressing it, what we're talking about is mitigation and adaptation. So those are two separate things, but we'll be covering that from a big picture. So thank you very much for this. I understand there was also a talk today on The Current, which is a show, I think it's Matt Galloway hosts it with the CBC. So apparently they were talking about something to do with climate change. I was off wandering in the woods with my pooches, so I missed that, unfortunately. So that good news also will come around next week as well, because we'll be talking about the effects of media, and we'll be looking at the big question of money, how that influences what we do with the climate crisis. So that having been said, today what we're going to be looking at is the past. We're going to start with the extreme past and work up to the present. What we're trying to do is look at what has influenced the climate in the past. And the Earth has had, for the most part, 4 billion, almost 4 billion years of life on the Earth. It depends on the estimates. Some are saying 3.5, some are saying 3.8, and some are projecting that life could have been here as much as 500 million years after the formation of the Earth. So we need to understand what the constituent parts have done. Right now, when we talk about the effects of carbon dioxide or methane or methane, depending on how you pronounce it, or the various oxides and water vapor in the atmosphere, we have to look back at the climate record to see the correlation. And is there a cause and effect? It's important to point out the difference between correlation and cause and effect. Correlation would be Switzerland has the highest chocolate consumption per capita in the world. It's also got the most Nobel Prize winners in physics per capita in the world. And you can draw two graphs and you will see they correlate. But it's not a cause and effect. As much as I'd like to say, I've been eating a lot of chocolate recently, it's not a cause and effect. Or maybe Albert Einstein did consume a lot of chocolate. I hope he did. So what we're looking now is at correlation. We can say, okay, carbon dioxide's going up and temperature should go up because the experiments tell us this, this, and this. Well, if we look at the historical record of what has happened, we can then get closer to cause and effect. Is in fact carbon dioxide a driver? And if so, how do we address it? So paleoclimate will help us put into context the variations of the climate. So it's really important to understand what has happened in the past in order to address what may or may not happen in the future and our input. And so we're going to be looking at various tipping points today. We're going to be looking at various agencies that react very strongly with the climate and into the weather. So without further ado, also, I think today we'll also be posting the questions that from the audience out in Cyberland that will be popping up, and I'll have to read it. If you have any questions, just put up your hand. We'll stop, and I'll try to remember to repeat the question. If you could stand up, as has been mentioned, for the microphones, so that everybody, there's no open questions right now. That'll appear. So if there is a question popping up, Bill or Bob or everyone will let me know. So context is everything. When we start looking at the deep past of the Earth, what's happening in the climate today has to be put into context into what has happened in the past. In other words, we are not unique. Our inputs, whether we're talking about carbon dioxide or methane or the reaction of temperature to the various greenhouse gases, the insulation of the sun impinging on the Earth, has a continuous history. And what has happened in the past, if we map out how that works, it should happen in the present and in the future. And so right now, life has been part of this matrix that is interacting with the Earth. The biosphere has become an incredibly important part of how the climate is affected. In that time, it's also important to point out, even though there's been a continuous tapestry of life from the first organisms that we can date ourselves back to 3.8 or 4 billion years ago, 99.9% of all species have gone extinct. And so their input and relationship, that's fewer than 1 in 1,000 have survived. That relationship to the climate is really important. And so we're going to begin with outlining the biosphere and its relationship to, wrong one. Oh, back. Here we go. There we go. Life in the Earth's chemistry. There's a feedback mechanism between life and chemistry of the Earth's air. And this first one that we're going to talk about, I find absolutely fascinating. In its simplest terms, the interrelationship can be called the Gaia hypothesis. And back in the 70s, one of the proponents of this, who laid this structure out, was James Lovelock. He died recently, about a year ago. I think he was 103. He had lived a long, long life. And he watched his theorization of the Gaia hypothesis, the interweaving of life, the tapestry, the feedback mechanisms of life into the atmosphere. He watched it go from being accused of having a crackpot theory to something that actually appears to exist, that it's becoming more and more referred to in scientific papers as a mechanism that is important for us to understand how things work. And in a nutshell, this Gaia hypothesis can be summarized by something called daisy world. And so he was trying to explain how this works. How does life interact? And he said, let's imagine that we have a planet. And there's a star, very similar to our sun, shining on this planet, which is very similar to the Earth. And you've got the only population on this particular planet are daisies. And they come in two forms. One is a white daisy and one is a black daisy. So what happens in that particular planet? And let's hypothesize that the planet starts to warm up for one reason or another. Could be volcanoes, could be the sun is increasing. So what would happen to the population of white daisies and black daisies? And if it gets too hot, we know that black will absorb more light and heat, and white, with a higher albedo, will reflect it. So if it gets too hot, the black daisies will find it very uncomfortable to live, and they will die off, and the white daisies will proliferate. And in addition to that, with the white daisies proliferating, their albedo, which is very high, which is white, on similar terms to what clouds are or snow is, would reflect back a lot of the light and subsequently the heat into outer space, and the planet would cool. And then if it gets too cold, assuming that all the black daisies didn't die out, it gets too cold for the daisies, especially the white daisies. The black daisies can absorb more light and heat, and they start to proliferate. And this balance ensues, this little tug between, is it too hot? Is it too cold? And will there be more white daisies or black daisies? And how do they interact with this temperature? In a nutshell, that's what Gaia is about. It's saying that various species interact with the environment and relate to the environment and actually modify the environment. So Daisy World was Lovelock's way of looking at things. And he had a couple of simple graphs there, and you can see, the relationship between the white and the black and the temperature between the two graphs. So what you're trying to do is keep a habitable temperature, not letting it get too hot, not letting it get too cold, and it's all because of daisies. So maybe we should be planting more daisies. So he called it the Gaia hypothesis, and Gaia comes from Greek, which means earth, and it's an illustration basically to say this incredible tapestry of life has existed for 3.8, maybe 4 billion years, maybe 3.5 billion years. But in that time, the climate has oscillated back and forth between what we call ice house Earth and hot house Earth, but it's always come back. It's always been in that stable equilibrium. There's never been a runaway greenhouse effect, not like on Venus, where probably there were oceans up until about 1 billion years ago. Venus is very similar to the Earth. But 1 billion years ago, the sun was much cooler than it is now, and Venus had predominantly carbon dioxide atmosphere, very greenhouse intensive. And as the sun got brighter, the Venus absorbed more heat, and eventually the oceans all evaporated, and you wound up with the sulfur dioxide clouds that we see today. And Venus has a runaway greenhouse effect. Now, that did not happen on Earth. As far as Mars is concerned, we're also thinking that it had water, but it was too small to hold on to its atmosphere. And it also didn't have a magnetosphere to protect it from the type of radiation that would disassociate oxygen and water molecules and ozone and then bleed out into outer space. So right now, the bar level on Mars is about 100th of what it is on the Earth. It's about 10 bars. On the Earth, we're at about 1,000 bars, or 1 kilopascal, or 100 kilopascal, sorry. So Lovelock and Margulis and others posited that this is a self-regulating system. It's a system that takes care of itself. And when something becomes too predominant, something else happens involving the biosphere, the atmosphere, the hydrosphere, and we're talking about oceans here, and the pedosphere, which is the land. They're so tightly coupled that they influence the temperature and the conditions on the Earth so that life can continue on. It's not a conscious mechanism. It's not something where Gaia says, oh, geez, it's getting too warm. I think we're going to have to do something. This is something that relates to the speciation that we have on the Earth that interacts with everything. Why this is important is because we are now looking at massive changes, including changes in species. And we're going into areas that we don't have a lot of information about. And the early part of the Earth's history, you have to take it with a grain of salt because the analysis is very, very difficult. Rocks that are 3 to 4 billion years old holding information are very difficult to interpret. So this system as a whole called Gaia seeks a physical and chemical environment that's optimal for life. And it's life's integration into that provides this habitable world that we live in. So let's talk about the first atmosphere. How did we get to this atmosphere that we're breathing? This didn't exist 4 billion years ago. The atmosphere we have today is completely different from what it was like when the Earth was formed. In the first half billion years, the Earth was accreting because of asteroids and comets and getting larger and larger. And it consisted basically of the gases of the solar nebula. And that means you're looking at hydrogen, helium, some of the lighter elements. In addition to that, nitrogen, carbon dioxide, that kind of thing. But we got smashed about 500 million years into the formation of the Earth by a gigantic asteroid, almost the size of Mars. And we're pretty certain about that. It actually created the moon. So it smashed into the Earth, destroyed everything, pushed away all the atmosphere, and created this new atmosphere, the second atmosphere, about 4 billion years ago. The Earth was highly reactive, so we had a lot of volcanic activities happening. And so with the remoltenization, I don't know if that's a real word, but I just made it up. As the Earth became molten again, it started to outgas various other gases. And we were looking at predominantly carbon dioxide and nitrogen that were coming in. The Earth is too small to hold hydrogen or helium to any extent. It basically, the gravitational forces are not enough to keep up with the kinetic energy at the temperature that we have on the Earth right now. So most of the hydrogen and helium that the sun was formed out of and that we see in the gas giants in Jupiter and Saturn really don't exist on the Earth. So, and a lot of the hydrogen was gobbled up by oxygen to form water. And so all the water that we see here is on the Earth right now is actually older than pretty much all the rocks on the Earth. The oldest stuff that we have on the Earth is the water. And it's been around even after it was there before it was smashed by the asteroid. So the importance of the second atmosphere is that life evolved in it. We don't know if life evolved in the first atmosphere. I mean, it was just so catastrophically damaging to have a Mars-sized planetoid hit the Earth that everything was destroyed. Anything at that point, we just can't read. There are no rocks left over, but we do see a mass in the Earth, in the mantle core of the Earth, that is probably the remnants of this giant body that hit the Earth. But after that settled down, we had a lot of carbon dioxide in the atmosphere. And the temperature was warm enough so that the oceans could exist at the triple point, which is they existed as liquids, they existed as solid and gas. So we had ice, vapor, and liquid in the oceans, pretty much carbon dioxide, nitrogen atmosphere. there was probably a huge amount of carbon dioxide. We don't know exactly how much there was, but it could have been as much as 30 or 40% of the atmosphere would have consisted of carbon dioxide, which is probably a good thing because the sun was about 70 to 60% the light power that it is now, because the core of where it's burning hydrogen, it's called a proton-proton reaction in the sun. I have to go back to my undergraduate days to remember my astrophysics, but there's a shell around the sun, in the core of the sun, that is the boundary of where hydrogen is being synthesized into helium, and that's growing outwards. And so as the hydrogen gets gobbled up, that sphere gets larger and larger inside the sun, and the sun heats up, and the sun gets brighter. And so we've only got about, the estimation is, another 4 billion years before the sun goes nova. So it's going to come to, all the good times are going to come to an end one way or another. I don't think I'll be around 4 billion years from now, but that is going to happen. They're theorizing that about 1 billion years from now, it'll be too hot on the Earth for life to exist anyhow. So it doesn't matter if the sun goes nova from that perspective. So life developed really quickly. We don't know why. It may be Hoyle, Bondi, and Gold were 3 astrophysicists who posited what was called panspermia. Panspermia is that life is ubiquitous in the universe if you look at all the basic carbon, nitrogen, oxygen, hydrogen makeup, that you put it together and they bump around, they will inevitably lead to proteins, amino acids, and eventually life. We haven't discovered any other place that has life, but that's our thinking, is that as the James Webb and the Hubble telescope gather information, as well as the overwhelmingly large telescopes, they're called owls, look out to the exoplanets, there is a good chance that we will find that there is life on other worlds that is based on carbon. And carbon is a really important thing. Carbon is important to life because it is the most variably reactive element in the periodic table. We like to think silicon's really neat, but carbon is spectacular. It has 4 valences. It can bond with anything pretty much. And it forms these incredible chains of molecules. And we see it in plastic. We see it in life. We see it in DNA. Carbon is the most important thing. It comes from carbon dioxide. Life started to evolve, and the first creatures were called anaerobes, like blue-green algae. And these anaerobes took the sunlight, and they had basic photosynthesis. And you can see that in the mitochondria of these anaerobes. When they went from prokaryotes to eukaryotes, they had a field day. For about 1.5 billion years, they sat in the oceans, created these vast mats of life, and ate. That's all they did. They ate and made more little anaerobes. And these little anaerobes were in the quintillions. And they had one downside. Let me just go to their photosynthesis meant that they spit out oxygen. And if you know a little basic biology and chemistry, you know that oxygen is the second most reactive gas in the periodic table, just slightly better than fluorine and much less dangerous than chlorine. It corrodes everything. It rusts everything. If we didn't need oxygen to live, it would kill us. The oxidation process is probably what relates to our aging. We have oxidants which degrade everything. So they spit out all this oxygen, and they did what we used to do, is just throw their garbage all over the place. It went out into the water, and then was absorbed into the water and went down into the sediment. And the carbon dioxide level started to come down. and it started to get a little bit cooler as the sun started to warm up, which was a good thing. But the oxygen in the atmosphere started to build up. And at first, the oxygen reacted with various metals like iron. And we can see the banded iron in various sediments that are 2 billion years old. And this continued on, this incredible eating of carbon dioxide through the photosynthetic process and the spitting out of oxygen into the atmosphere. This is called the prebiotic atmosphere, by the way. Why it's called prebiotic, it's really pre-evolutionary. Once this life established, these anaerobes, it was pretty boring. So roughly 1 billion to 1.5 billion years, nothing much went on except you had this sludge living in the ocean that was keeping the Earth's temperature in balance. As the sun got warmer, they were sucking out carbon dioxide, putting out oxygen, and looking at the sedimentary rock, we can see where this happened. And at some point, all the oxidation processes came to an end. And we had what is called the Great Oxidation Event. And this is where the party starts to end for the anaerobes. So about 2.4 to over the process of 100 billion years, this oxidation event in the Siderian period, you can see that little bump where it says 2 on the bottom. There's stages, and you can see that bump of oxygen. Before that, there's no free oxygen in the atmosphere. And then all of a sudden, oxygen starts showing up. And we're looking at oxygen contents of anywhere from 1 to 5%. Right now, it's currently at 21% of the atmosphere. And at the end of that stage, it stayed there. And the anaerobes had a lot of trouble because as the oxygen built up, they died. And that was a bit of a problem for them. As they died, that meant other creatures that certain anaerobes were able to adapt and metabolize the oxygen. And in doing so, we found out that oxygen, from a life standpoint, it increased the metabolic rate of the organism by a factor of 10 to 100. It outcompeted the anaerobes. So these new prokaryotes and eukaryotes, single-celled organisms, were actually able to metabolize the oxygen, live within the oxygen that was there, and they gradually started to supplant the anaerobes. The anaerobes continued to photosynthesize the carbon dioxide. Carbon dioxide levels continued to fall, but now they had competitors. And then, getting back to Gaia, this is showing the balance. It's very similar to Daisy World. Like, you have one particular organism that comes to predominate. It offsets the temperature a bit. The temperature remains in the habitable region, but with the reduction of CO2, the Earth started to get hotter, and as it got hotter, the anaerobes also started to die out. Sorry, before I get to that, before the heat, as the Earth started to get cooler, we then started to get an effect called the first mass extinction. And this mass extinction was the stromatolites and the various anaerobes that died out because of the Great Oxygen Event and the poisoning, which led the way to a biosphere that was predominantly aerobic. And normally, we don't count this as the first great extinction because it happened so long ago. And because we just don't have a whole lot of information. Something that happened between 1 and 2 billion years ago, the crustal plates are constantly moving into each other, and the ocean sediment is disappearing. And so the ocean sediment that we have is no older than 300 million years. So what happened 1 billion years ago is very difficult to ascertain. You actually need it in certain types of continental rock, which there's not a whole lot of. in Canada and Australia. I believe we have the oldest sedimentary rocks. So now, moving on to the Paleoxygen record, you can see that something really strange happened between 700 and 600 million years ago. And the oxygen jumped way up, and the carbon dioxide correspondingly fell. And as the Earth adapted to that, or tried to adapt, with the depletion of carbon dioxide, we wound up with something called snowball Earth. And the Earth at that particular time was completely covered by ice because the carbon dioxide had been just about virtually insufficiently necessary to keep the Earth warm. So what you have is an event that almost did in life. There were only a few places where life could exist in snowball Earth. There was no more photosynthesis happening, but we did have deep trenches and we did have plate tectonics. And that's where the plates came together. And that is where you had tube worms and various other complex life. And that's also where volcanism happened. So you had a lot of volcanoes erupting, and within 50,000 years, after snowball Earth having lasted almost 100 million years, we had an influx of carbon dioxide, the temperature shot up, and we had a complete change in the oxygen record. This is what the Earth would have looked like 600 to 700 million years ago. And the cooling would have covered all of this with ice. The entire oceans would have been covered with ice. Even in the polar regions, some of the thinking, it's still controversial, but some of the thinking is saying that we may have had as much as 100 meters of ice in the equatorial regions covering the oceans. So there was no possibility of photosynthesis happening. It was only happening in the tectonic trenches. So then we had a period of hypervolcanism because that's being generated by the Earth's core. And there was a massive melting of the ice. They figure it melted within 50,000 years. All the ice melted and things began to change in what is called the Ediacaran, just before the Cambrian period, some 600 million years ago. This is where the oxygen sinks are filled. The oxygen really starts to build up. We still can't breathe the air. There's not enough oxygen there for us to breathe, but it's building up in the atmosphere. And this is where the biovolume goes crazy. It increases 100-fold. That by biovolume, we mean that the amount of mass of the Earth in the biosphere goes up by 100. And that's all because of oxygen. And this is what it looks like in the Ediacaran. And you can see all the continents are Laurentia, Gondwanaland, making up, I guess, one of the massive supercontinents called Pangaea, and then you had one giant ocean called Panthalassa. So when we look at, we're going to take a little divergence here. So we get the great oxygen event, we get the proliferation of life, and then from 600 million years to now, oxygen builds up. And there is this tug back and forth between oxygen and carbon dioxide. And because of snowball Earth, it's important to talk about the temperatures of the ocean. And that's important because 90% of the Earth's atmosphere heat is tied up in the oceans. It's more important than the atmosphere itself, really, except for the fact that we're so people-centric. We tend to think the atmosphere is the most important thing and not really think about what's going on in the oceans. And that's why this is important, that we're getting money going into ocean research, because that's where the climate really resides. So you can see over the last, and this is for the Phanerozoic, which starts from the beginning of the Cambrian right through the Paleozoic to the Mesozoic and Cenozoic, and we wind up with various temperature profiles. And where it spikes, goes up, that's called hothouse Earth. And where it's down, that's called icehouse Earth. And currently, if you look at the right-hand side of the graph, You can see that it's colder than it's been since the borderline of the last major glaciation in the Ordovician-Silurian extinction band. And you see that those glacial periods are unique. And it hasn't been this cold in forever, almost 440 million years. And so you get various cold periods and various hot periods. And there's always this balance going on between the life, the chemistry, the sun, which relates to the temperature. And that's what we're trying to trace back to when we talk about the climate crisis. And the reason this is important is because these signatures tell us about the tipping points that we're facing today, which ones are going to be issues for us. So the Phanerozoic is the last 540 or so million years, 500 million years. That's what's important to us. But it's only a tiny fraction, only about 12% of the total Earth's history. We have just covered almost 90% of the Earth's life history and climate history, just in the first half hour, 45 minutes. And the oxygen levels at the start of the Phanerozoic were now starting to push upwards. And they were pushing up dramatically because there was so much photosynthetic activity. The aerobic creatures took over a large amount of the heavy lifting in the production of oxygen, specifically plants, but we also had plankton in the oceans that were not anaerobic. And so the anaerobes retreated. They went into areas that they didn't have to compete with the aerobic creatures. And these aerobic creatures were up to 100 times more metabolically active than the anaerobes were. So they couldn't really compete at all. But they still existed and they still produce oxygen. We find them under the earth. In the deepest holes, we find anaerobes and anaerobic creatures, little tiny microscopic creatures that are still producing oxygen. And so the oxygen level started to climb dramatically. Right now it's at 21%. Has anybody been to Joggins? If you haven't been, I recommend you go. The Carboniferous period, which happened about 300 million years ago, is where oxygen peaked. 35% of the Earth's atmosphere was oxygen. There was so much oxygen in the atmosphere that every thunderstorm wound up producing huge fires because of the lightning strikes. At 35%, there's a reason they tell you that when you go into a hospital and they've got oxygen, they tell you not to light a cigarette or a cigar or anything like that. It's very flammable. Your grade 9 chemistry would have, when you use electrolysis to split apart water and hydrogen, the hydrogen burns off, but the oxygen makes an ember burst into flame. And so in the Carboniferous, this is the time when the coal forests were laid down, and they were laid down because of the swamps and the fires. These forests were charred, they died, they fell down, were covered up by sediment, and their carbon didn't go back into the atmosphere. So this was a time of great coal swamps. This is where all our coal comes from, a lot of our natural gas, and some of our oil. And so our hydrocarbons that we are mining now, we're taking the sunlight of the Earth from 300 million years ago and putting it back into the atmosphere. So if you go to Joggins, you get to see these plants and you get to see these animals. And one of the offshoots of this is that insects and various arthropods and amphibians were able to grow hugely. There were dragonflies that were 2 feet across. And years ago, I had the chance to meet Don Reed. He's since passed away, but he was a self-taught geologist and paleogeologist, and he wandered his entire life in the Joggins area on the cliffs. They run about 20 miles or so, and he set up the first museum of the trees that were found in the cliffs. You can actually, they look like Corinthian columns, and some of them are 1 meter across, and some of them were 200 feet high. And he found so many, he was actually teaching the geologists at Dalhousie all about the paleontology of the Carboniferous. It's spectacular. It's worth going up to. It's only about 3 hours away, 3.5 hours. And the cliffs are just an amazing, it's a World Heritage Site. So if we look at the climate record and we start in the Phanerozoic, you can see that right now, off to the right, things are quite cool, and off to the left, they tend to be hotter. So the question then becomes, why are we so concerned about the Earth heating up? I mean, if much of the Earth and the Earth's history has been so warm, why are we so concerned about it? Because if natural processes brought us there, why would we care whether the Earth is warming up? And so the next part of this particular lecture is going to be talking, again, going back to what Lovelock and Margulis talked about in terms of Gaia, is the interface between life and the Earth's atmosphere. So we've got 500 million years of detailed climate data. The older stuff is more difficult to analyze than the more recent stuff. So we got a lot of recent things going on, but that's basically from the last our ice age. And so we don't see the tipping points that existed in the ice record or in records that are far more detailed. The further back you go, the greater the error bounds are. And it could be plus or minus 20 or 30%. So that is kind of an important consideration. When you look at atmospheric CO2 levels, for instance, 400 million years ago, they would have peaked at 2,000 parts per million. Right now, we're at about 420. And so you can see it's just a fraction. It's only 20% or slightly more than that, current levels during the Jurassic period. So CO2 in the Phanerozoic, it has been on a continuous decline. Whereas the oxygen is going up and going down, it peaks in the Carboniferous, starts to go down, goes up again, and then comes down again. And right now we're hovering around 21%. You can see during the Cambrian, the Ordovician, the various letters at the bottom start from about 540 million years ago, and they start with the Cambrian, and then they move off to the Ordovician, Silurian, Devonian, and then we wind up into the Mesozoic, age of dinosaurs, and then the Cenozoic, which is the age of mammals. So you can see how the carbon dioxide levels are falling, but the temperature remains largely stable. It is also falling, but within bounds, that the ice never becomes as extensive as it was during snowball Earth. And that's because of the interface with life. So that will be the second part of the lecture. We're going to take a 10-minute break and then move on. Now, before we do that, are there any questions? I don't see any questions coming up. Nothing. Okay, that's good. So the next part, we're going to deal with the extinctions and life interface. So it's all clear as mud, I take it. Can I have your attention, please? Okay, here we go. The second part. This is going to be a little bit longer than the first part. We're just setting up the groundwork for what we're going to be talking about, which is extinctions, and our own included in this because of the changes in the environment. Now, I've had a couple of requests for book lists or recommended books, and I was thinking of bringing part of my library in, but I think what I'll do is set up a reading list, and then it'll be posted on the site. There's some amazing books out there. And locally, one of the best that I read that relates directly to what I was talking about in this lecture, you can pick up at the Natural Museum in Halifax, which is, I think, down on Summer Street. And they wrote a book about a decade ago, which I think is sterling. It is wonderful. It's called A Billion Years of Life. And you can pick it up. There's a CD-ROM attached to it too, I think. I don't think anybody knows what a CD-ROM is anymore. But the book is outlines the billion years that we've been talking about. The basically billion years. It talks about snowball Earth. It talks about the Phanerozoic, the Mesozoic life, the conditions that life lived in, and it also relates a bit to what we've been talking about in terms of the chemical makeup of the atmosphere, carbon dioxide, oxygen, that kind of stuff. So this part is going to be about extinctions. What can we learn from the past record? So what has happened in the past leaves little signatures, and we can use various proxies. And if I'm going too fast, and sometimes I scurry down a rabbit hole and get caught up in that, if I go too fast, let me know. We'll slow things down, give you a little contextualization on it. The trouble with 12 hours of climate crisis lectures is it's not nearly enough. And so you try to condense into particular paths all the things that are relevant to this. And sometimes little whirlpools happen that are really important, but don't seem like they're important at the time. So extinctions, when we talk about that, that is an important part of the climate life interface. And as I mentioned at the start of the last lecture, at the beginning of the last hour, 99.9, more than that, % of all life has gone extinct. And it's the same thing that I was saying about the climate. Well, if it was hotter or colder before, why does it matter if it gets hotter or colder? Well, it's the same thing with life. If all these creatures have disappeared, and we're in the middle of another extinction, isn't this just part of the natural process? So why are we concerned about it? Well, what we see are certain signatures that pop up. So this is about extinctions, and particularly mass extinctions. These are events that are off the charts. We always have a background clutter of species coming into being and dying. The evolutionary process that Darwin was among the first, Darwin and Wallace, outlined, tell us that species adapt to certain environmental conditions and certain species don't. And the vast majority of those don't. And those that do are subject to mutation. There's something about it just slightly different. It's Daisy World again. Maybe I've got a little more black pigment in me than white pigment, and that makes it better when it gets cold because I absorb more heat. So I get to pass my genes on if I'm in the gene passing business, which at this juncture, we won't go into that. So a couple of guys by the name of Ropp and Sepkoski are the progenitors, speaking of passing their scientific genetics on. Back in the 1980s, they started talking about the fossil record and what it was telling us about how life had existed in the past. And they came up with, in the Phanerozoic, the last 540 million years, that there appeared to be 5 major mass extinctions. And these are not extinctions that, one species disappear. These are extinctions where 50 to 70 to 90% of the species disappear. They're just huge. And there are 5 of them. They occur at the end of the Ordovician, which is 440 million years ago, the end of the Devonian. The Ordovician would have been the age of trilobites. Anybody not know what a trilobite is? It looks like a little bug, a sow bug. You know, when you lift up rotting wood and you see those little multi-legged armored tank-like little creatures scurrying around. Well, trilobites dominated life in the Cambrian and in the Ordovician. And I'm just going to shut this off. My apologies. There we go. It figures. I never get calls. So at that time, trilobites, which are arthropods, they've got chitinous shells, multi-legs, eyes on the front, scurried around the bottom of the oceans. And if there was life on the continents, it was mainly mosses and ferns, and not much else than that. Life existed in the oceans, and it was the age of the arthropods and the sponges and that kind of creature. And then all of a sudden something happened at the end of the Ordovician, and all that life took a major hit, and we see it in the fossil record. All of a sudden, we look at the sediment above, and we don't see as many trilobites anymore, or we don't see as many sponges or bryozoans or brachiopods. So the end of the Ordovician was the end of the pretty much, you start to get into the Silurian, the age of fishes starts to come in. So these creatures adapted better than the arthropods to life in the ocean, and they became bigger and bigger. And you wound up with the age of fishes, and then which was the Silurian, end of Silurian into the Devonian. And then something bad happened 340 million years ago for the fishes in the Devonian, at the end of the Devonian, and they took a major hit. The placoderms died. The fish there was a fish called the Dunkel osteus, which was a placoderm that was reputed to be 10 meters long and had a head with giant jaws that was 3 meters. 1/3 of its length was just used to gobble up stuff. It ate sharks for dinner. It was the apex predator of the time, and it died out. I mean, it couldn't survive that kind of thing. So that happened at the end of the Ordovician. And then there was the Permian extinction, which happened. So you get to the end of the age of fishes, and then you wind up with the age of amphibians. And you had coal swamps. You had frogs that were, or amphibians that were the size of small Volkswagens. They were huge. They sat in the swamps and they ate whatever they wanted. The millipedes were 2 meters long. Centipedes were slightly smaller. You had cycads up to between 100 and 200 feet tall. And cycads are basically ferns, and they lived in the coal swamps. And you had insects that were able to metabolize the high oxygen at that time. Insects don't have lungs, and arthropods don't have lungs, and they don't have gills either. What they have are respiratory systems that rely on just the oxygen coming into small holes in their thoraxes and abdomens. And so in their body parts, they have small holes, and it actually interfaces with their blood vessels that way. They don't have mechanisms for pulling it in and out the way it works for lungs or gills. And so there was so much oxygen, they could become huge. The dragonflies were 2 feet across. It was just an enormous size of those particular animals. And then boom, something happened at the end of the Permian, and all these creatures died out, and the mammal-like reptiles died out. And then you had the start of the Mesozoic, which, if you remember Jurassic Park, they talk about Jurassic Park and the dinosaurs. Well, you had a major event happening between the Triassic, the start of the age of dinosaurs, and it lasted like, oh goodness, 165 million years. And at that boundary, then you had the Jurassic, and you can see the spikes basically. And then we had what's called the KT, which is the Cretaceous Paleocene. And Cretaceous starts with a C, but they put a K in there anyhow. So that's, go figure English. It's not my first language, by the way. It's true. And so those are the 5 major extinctions that Ropp and Zurawski were able to ascertain from the fossil record. They basically had to be mega aggregators. They had to filter all this information to figure out what had happened. And not only what had happened, but why it happened. This is where the life interface comes in. And so right now, we are concerned that we're losing species at a rate that is really disconcerting. And it's probably, I guess they're saying a million species, plant and animal, are threatened with extinction. And the rate of extinction is 1,000 times higher than what you would see in a normal period that's comparable to what we've been doing over the last 2,000 years. So 1,000 times higher is a lot. Those are 3 orders of magnitude. So we're going to relate the past extinctions to the extinctions that are going on now because it's related to climate change, climate crisis. So understanding the past extinctions is important because generally speaking, since the beginning of the Cambrian, you notice the curve of life, the number of species, the number of genre, the number of orders increases. And it has been increasing for 540 million years. The tapestry, the interweaving of life is going up until now. And this next extinction is going to put a little knot in this tapestry. And you can see the 2 graphs and maps there. It relates the 5 major extinctions as well as a whole pile of other extinctions that come up. And when Ropp and Zurawski back in 1982, their first book came out. And oh, by the way, I'm going to be making a reading list for you, and I'll bring it here next week, so we'll post that. When Ropp and Zurawski started with this, they had no idea that there were so many other minor extinctions. And they're trying to place everything into context. And I'm going to not jump too far ahead here. So in the overview, the KT was the most recent. That's the end of the dinosaurs. That happened 66 million years ago. And the Chicxulub asteroid impact is the most likely cause. So we think that's it. And we can thank Lewis and Walter Alvarez, father and son team. The Triassic Jurassic happened a little over 200 million years ago. Its probable cause is because of climate change and volcanism. The 2 sometimes go hand in hand. And there's a smaller chance of asteroidal impact. If you look at a map of Quebec, you'll see Manicouagan, and there's a lake, and it looks like, oh, that belongs on the moon. That looks like a crater. And that is an asteroid impact that is the right time for that particular extinction. Now, whether or not it was as catastrophic to life at that time, it probably didn't do life any favors, but it didn't have the right flavors that the Chicxulub Yucatan impact did. And we'll go through that in a second. The next one, 251 million years ago, is called the Permian, 252 million years ago. It's called the Great Dying. What happened to life at that time is absolutely catastrophic. Everything was affected. And volcanism, we call, happened in Siberia. They're called the Siberian traps. And most of the researchers that were looking at geology 100 years ago tended to be German. Alfred Wegener, who was doing plate tectonics or continental drift. And they used German language. And in German, steps are called Treppe. And when they looked at the volcanic basalt that had been laid out in Siberia, they could see that it came in layers and it looked like steps. So they called them treppe, and when we picked it up in English, we could just call them traps. So they have nothing to do with traps, they have to do with steps. So you can see the various steps that happened in the volcanism. And the Permian is probably one of the most important examples that we're going to review in terms of what we're doing to the climate. And then the late Devonian, 340 to 372 million years ago. And as we move further back into the past, the fossil record is not nearly as complete. A lot of it gets buried. And I mentioned that our crustal plates, the plate tectonics, are moving all the time. So the ocean, what the ocean water rests in, the ocean crust, is disappearing every 200 to 300 million years. So anything that's there gets pushed into the mantle and it gets eaten up. So the fossil record, that kind of thing. The continents are the froth. But the trouble with continents is that complex life really hasn't been there for more than 400 million years. If you go back to the further fossil records, the further proxies that we use, they're not there. Most of it's in the ocean, and unfortunately, a lot of the ocean gets subsumed by plate tectonics. So we talk about these mass extinctions, but we're not as certain as we are about what happened and how it happened as we are with something like the KT disaster, which killed off the dinosaurs. And then we're going to look at the end of the Ordovician, which happened about 445 million years ago. And that one is interesting to us because its most probable cause is massive climate change during icehouse Earth. So all the other ones, you look at the Triassic, you look at the Permian, the late Devonian, they happened when the Earth was basically hothouse. So the conditions are slightly different. So the one that is most relatable to us is also the one that's most distant to us. It's almost 500 million years away. So a lot of the evidence has disappeared. We okay so far? There's also another event that we're going to examine, and it's called PETMA, the Paleocene-Eocene thermal maximum. Scientists are nothing if not clear about how they label things. So 55.5 million years ago, there was this enormous spike in temperature. And this was about 10 million years after the dinosaurs had disappeared. And there was a massive release of CO2 into the atmosphere, and it happened in 20 to 50,000 years. So you had this great influx of CO2 and particulates and sulfur dioxide, and it lasted, this warm period, the PETMA, lasted about 200,000 years. And the global temperatures, surface global temperatures, were up to 9 degrees warmer than they are today. Some of the ocean temperatures in and around the equator were as high as 40 degrees Celsius. So that's pretty warm bathwater. And that creates certain problems. A total of 12,000 gigatons. Now, everybody knows what a gigaton is. Gigatons of carbon were released at the rate of about a quarter of a gigaton per year at a rate of 50,000 year duration. Like that's just a huge amount of carbon dioxide. In comparison, right now, humans are releasing 1.6 gigatons increase of carbon into the atmosphere in 2011. And so if you compare, because this is relatively recent, I know 55 million years ago doesn't seem like it's recent, but I remember it well. Humans are releasing about 10 gigatons of carbon each year, which is about 37 gigatons of CO2 each year. And we'll have released what happened in Petma over 50,000 years, 20 to 50,000 years, we will have released in 1,000 years. So our rate of putting carbon dioxide into the atmosphere is probably 20 to 50 times greater than what happened during this catastrophic event when the Earth's temperature spiked. And this is where we start talking about correlation versus cause and effect. So the correlation is, yeah, the carbon dioxide went up and the temperature went up. The cause and effect is, did it relate? Did the carbon dioxide increase relate to the temperature increase? And we think it did. We think it did dramatically. And Petma is interesting because it is the beginning. So you had this massive spike at the Paleocene-Eocene boundary. These are two epochs epochs within the Cenozoic. And Cenozoic means recent life. Zoic is life, Ceno is recent. And they occurred during the first epoch at the end of the Paleocene and the beginning of the Eocene. The Eocene is notable in that halfway through, you wound up with this heating with Petma. Temperature then stabilized, took 200,000 years to do it, but then the temperature gradually started to fall. And in the last 35 million years, from the middle of the Eocene to now, the temperature has done nothing but fall. And we've accumulated ice in the Antarctic, in the Arctic, in the mountaintops. And so what's going on? This is what we're trying to relate. What's going on? How do we slip into Icehouse Earth? What was it that brought us there? And Petma is an important signature for this. So on average, what happened during the Paleocene-Eocene thermal max? Because the temperature went up, precipitation went up. A lot more rain started to happen. And with a lot more rain, if the temperature goes up, you have more greenhouse effect because the major greenhouse gas is water vapor. It's even more important in total than carbon dioxide, but it's incredibly variable. In the Arctic, you have no water vapor, and the Antarctic, because it's too cold. The water freezes out. There's no water in the troposphere. So having a warm temperature creates more cloud, but it also creates more water vapor. The cloud reflects the sunlight. It's this kind of weird balance going on. So the precipitation is a key. So we know the precipitation had increased. And we also know that there were radical changes in ocean currents because any of the ice that may or may not have existed in the north, and there probably wasn't much there, disappeared, ocean currents changed. And with the increase in the ocean temperatures, if you took a temperature profile of the ocean right now, the bottom of the ocean is at 4 degrees Celsius. Water is incredibly unusual. At 4 degrees Celsius, water achieves its maximum density. So if you have water at 30 degrees Celsius and water at 4 degrees Celsius, the water at 4 degrees Celsius will sink to the bottom, and the 30-degree water will stay on top. At the same token, if you have water at 1 degree Celsius and at 4 degrees Celsius, the water at 1 degree is less dense and it'll stay on top. That's why ice forms on the top of water and why ice floats. If it didn't do that, there would be no life on the Earth. And so with the increase in temperature, you have different flows. And the profile shows that the bottom of the ocean during the thermal maximum, Petma, was 10 degrees Celsius. And the top of the ocean in the tropics averaged at about 40 degrees Celsius. And if you look at the polar regions, especially the North Pole, since the continents were roughly in the same position, you had water temperatures of 20 degrees in places like Banks Island and Baffin Island. And we actually have found forests and fossils of crocodilians and hippo-like animals that lived in the darkness during the Petma, the Paleocene-Eocene thermal maximum. Even though there was 3 or 4 or 5 months of total darkness and various insulation, the average Earth temperature was enough to keep it in a semi-tropical temperate environment. So the ocean temperatures were so warm, and these are surface temperatures, and even the bottom temperatures were very warm. This also meant that the ocean could not hold much gas. So anything that was dissolved into the ocean in the form of gases, especially the sulfides and cyanides. We have hydrogen cyanide, really bad gas, and hydrogen sulfides. Both of those gases we find in sewage. And I don't know if you remember, about 20 years ago, it's called silo gas as well. And it's why you should never, ever venture into sewers without complete coverage. The molecule is small, both hydrogen sulfide and hydrogen cyanide, and it's incredibly toxic. It goes actually through your skin. And about 20 years ago, they had an awful occurrence in Saskatchewan where a farmer went into his silo, which had been he'd taken all the corn out, but there was still some gas left there. And all the silos have giant venting machines so that you can go back in there and work in there. And the venting is to get rid of these dangerous gases. And he went in without venting properly. He didn't come out, and his son went in. And he didn't come out. And then another son went in. In total, the entire family died. I think there were 5 or 6 of them, plus a number of neighbors who went in as well. You can get overcome by these gases in as little as 30 seconds, and it goes through your skin. You don't have to breathe it. So during this time, all these gases were venting out of the ocean because it's so warm, it can't hold it. And so you wind up with basically silage gases. And you had also anoxic zones, so there wasn't much oxygen. Anoxic means no oxygen. And so you had places in the ocean where there was no life, or just anaerobes. I guess it'd be the anaerobic revenge for the great oxidation event that we talked about in the last lecture. And acidification happened because the carbon dioxide would bond to create carbolic acid. And carbolic acid is what you get when you put carbon dioxide into water. And it decomposes shells. And if you're a shelled animal, like a snail or a lobster, it actually eats. It takes the calcium carbonate and breaks it apart, and they die. And there was also sea level rise because of the thermal expansion. It was quite significant. So ocean levels were probably on the order of 250 to 300 feet higher. And that meant that you had much less continental area. And there was a mass extinction of the deep ocean animals, the benthic foraminifera, specific types of. I don't think that was me. I'm sorry. And with the warming also, there's something called methane clathrate. This is where methane has been formed at the bottom of the ocean, and it sits for the cyber folks out there. It's just a bell that we have going on outside, a buzzer for someone who wants to get inside. Pardon me? So the clathrates then, because when the ocean warms up, wind up bubbling through the ocean, and you wind up with methane going into the atmosphere, which is about 50 times the greenhouse gas that carbon dioxide is. And that adds to it, and you had no polar ice. So the albedo changes. And water is a much greater absorber of light than snow is. And as I mentioned, the bottom ocean temperature was 10 degrees Celsius compared to 4 degrees currently, which is at the maximum density. So we're starting to connect here. We're seeing tipping points. We're seeing that gasification of the oceans, rising sea levels, mass extinctions, anoxic zones, increased precipitation, all of that is starting to be a cause and effect between the environment and between the between life. Okay, so we'll go back now 10 million years from there to the KT mass extinction. And this one is really talked about a lot. We know that this asteroid came in, but what a lot of folks don't realize is the specifics of how it came in and why it was so catastrophic. First of all, the asteroid did not impact the Earth on a perpendicular plane. It came in on an oblique plane of about 30 degrees. The second thing is that the water was shallow. So at that particular place, it wasn't the deep ocean. So a lot of the absorption went directly into the sediment. And the sediment was predominantly a sulfur deposit. And so what happened, it was a perfect bad storm. Came in obliquely, ground up all this nonsense, sulfuric acid, particulate matter, and because it was oblique, it pushed it off into the atmosphere. And you can see how that works. If it's coming in obliquely on the surface of the Earth, a lot of the energy is going to throw the various rocks and impact. You can actually see some of them up in Sudbury from a previous impact. They're called shatter cones, where pieces of the crust is broken up and they fall back down again. And the problem is when they fall back down into the atmosphere, they're coming in at hypersonic speeds. So they're coming in at speeds that are miles per second, and they ignite. And so when it's not only in and around the Yucatan, but much of North America was the beneficiary of all these shatter cones that then were superheated, hit forests, and you wound up with massive forest fires raging all over the place. And then all that particulate matter, because of the intense heat of the forest fires, wound up getting into the stratosphere. And we know that's important because if it stayed in the troposphere, if it had been a vertical impact, it would have just flattened out and it would have stayed in the troposphere, and the rains would have washed the particles out and they wouldn't have stayed there for years. What happens with an oblique trajectory of this asteroid, it pushes all the particulate matter up into the stratosphere. And once it's up there, it ain't coming down again because it's not going to rain out. Nothing to force it out. There's no condensation nuclei, which is what happens in the troposphere. They're called even the small particulates will then become condensation nuclei, which will form raindrops, mist, raindrops, that kind of thing. And you'll wind up with thunderstorms and it washes things out. You get that clean air feeling after a good rainfall. So this impact from this asteroid was a perfect storm. If it happened to any place else at any other time, even a day later, the dinosaurs would not have died out. And with the dinosaurs, we would not have had, not dying out, the small mammals would have not been able to lead to us, and the dinosaurs, I'm sure, wouldn't have been talking about climate crises. So they wouldn't be having this lecture because they were smarter than that. So this led to this massive extinction where 75% of all species died off, including dinosaurs, pterosaurs, the ichthyosaurs, all the giant creatures of the time all died out. It was severe and it was sudden. And 75% of all species died. And that means fossil record tells us there was nothing for 5 million years afterward. It took about 5 million years for life to begin to recover. The mega tsunami was 100 meters plus. If it had happened in the deep ocean, the mega tsunami would have been almost 3 miles tall, 4.6 kilometers. And that would have created a different type of devastation, but it would have also put out a lot of the forest fires, which is, you imagine a 5-kilometer wall of water impinging on the coast. It's not a great thing, but at the same time, you won't have all that soot and dust going into the atmosphere. So if you're fortunate enough to be a dino living on top of a plateau inland, you're going to survive, and the plants are going to survive because they're not going to burn up. So it also may have triggered another volcanic outburst in India and in, they're called the Deccan Traps. Treppe, again, steps, and they're the second largest volcanic eruptive, excuse me, eruption in the Phanerozoic. And so we see evidence of these traps, and this asteroid may have created that particular impact. What are we doing here? I don't want to run out of time. And so there was a massive fire, and then with the particulate after the heat came the nuclear winter. The scenario where you punch all this stuff up there, all the plants dies, the herbivores die, with the herbivores dying, the carnivores die, and there's pestilence, death, and destruction, screaming and yelling, all that kind of stuff. And I'm sure they yelled. So just to give you an idea, it was 100 teratons of TNT input into the ecosystem. And when we talk about climate change, that's what we're talking about, is energy input. And so it comes in, if you're into the zettajoule understanding, it's 420 zettajoules, which is billions and billions and billions and billions and billions, or 1 billion Hiroshima, Nagasaki bombs. I hate using that analogy because that's one of the great horrors of the 20th century, that the West chose to detonate nuclear bombs and devastate people with them. But you can see, you get a visualization of the impact that this asteroid had. And it was roughly 10 kilometers across. I mean, when you compare it to the size of the Earth, it's like a little pinhead. So the nuclear winter lasted for 1 or 2 years, enough to kill off all the plants. Temperatures dropped almost overnight to 7 degrees, where there were no fires. And the carbonate rock created acid rain, which also killed all the soil biomes. So acid rain leaches into the soil, into the land, worms, crustaceans, insect, everybody took a hit. Wasn't pleasant at all. The next one on the list, again, happened in the Mesozoic, and this is during the height of the latest conglomeration of all the continental crust on the Earth. And we're talking, this is called Panthalassa, which is the ocean, and Pangaea, which is the Earth. So all the continents, and this is running from the North Pole to the South. So the top is the North Pole, the South is the South Pole. So you can see how big that continental mass is. And then everything surrounding it is ocean. So all the crustal plates had come together. And this was a big extinction. If anything, it was bigger than what happened during the KT. And up to 75% of the species became extinct. And the last of the trilobites died at this time. Poor trilobites. They had existed for 300 million years almost. And this was their final song. Again, because this is such a long time ago, there's no clear, definitive cause and effect for this extinction, but they're looking at gradual climate change. They're saying something happened here that's ocean related that created a number of tipping points. And these tipping points all came together. And this is where we start to get the idea that the climate crisis isn't one particular thing or two particular things. It's a number of perfect storms happening together that all come together that switch us into a different climate regime. And if it happens really quickly, it's like a switch. And so in this particular case, what we're learning from the Triassic-Jurassic extinction is that this switch gets activated from from many different places. It could be climate, it could be volcanism, it could be sea level related, it could be outgassing. And it's important to remember that we're talking about hothouse Earth. So the climatic conditions were different than they are now. Not a whole lot of sea ice happening there. And there is some evidence for asteroidal impact, as I mentioned, Manicouagan, and there are other sites. I think in Australia, there's one called Bedout, which is in the ocean crust. And because it's in the ocean crust, it's not really observable because it's underwater. And it's also in a place where the sediment is being eroded by the ocean water. Okay, this one is probably the most important study in terms of past climate. This is called the Great Dying. This is where life almost ended on the Earth without putting too fine a point on it. This happened 251 to 252 million years ago, a quarter of a billion years ago. And this one was catastrophic, off the charts. And the consensus now, because it's so long ago, we think it was carbon dioxide emitted by volcanism in the Siberian treppe, which elevated temperatures, created the acidification of the ocean. So if you lived along the oceans at this particular time with the hydrogen cyanide and hydrogen sulfides coming off, and you were a critter wandering around, you would die very quickly. And this was from the outgassing from the warm temperatures. The seafloor has taken up about 90% of the evidence that we have to this the Great Dying. And CO2 levels may have been as high as 8,000 parts per million. We think the PETMO was bad at 4,000 parts per million. Well, 8,000 parts per million is the highest level of carbon dioxide through the Mesozoic, and then it started to fall after that. So it peaked at 8,000 parts per million. And when you think right now, we're at 420, just about 20 times higher in carbon dioxide. And you would actually, and there was also a spike in oxygen levels as well at this particular time. So if you took a breath, you wouldn't really notice as much, but it was an important constituent of the Earth's atmosphere at that particular time. The importance of outgassing cannot be overstated. We're really concerned about this. And this is why the Dow ocean studies, the oceans make up 70% of the Earth's surface. And we know less about the oceans than we do most of the planetary surfaces in our solar system now. It is such a difficult place to visit for any extended periods of time. And we don't live there. And we tend to just treat it as a resource, take what we want, do what we want to it, and then walk away. With the temperature being as warm as it was, with the carbon dioxide levels being as great as they were, the dissolved gases outgassed, and that includes methane. The ocean's also acidified again, which is what we're noticing right now. The acidification rates of the oceans are increasing. The anoxic zones are increasing. That's places where there's not enough oxygen for creatures to live. And there are actually certain types of phytoplankton, not phytoplankton, just plankton, red algae, that actually seek out and create anoxic zones. When the temperature goes up, it takes as little as a couple, they lie, it's fascinating again, how life creates its way of dealing with things. But there's a red algae that is very, very toxic. We notice it in clams, mussels, that kind of thing. We had a couple occurrences in polluted areas where people ate mussels that were contaminated with this red algae and died, and some of them went blind, some of them lost the use of their arms, legs. So that's a really important consideration for the health of the ocean. So this red algae actually if a fish swims over it and poops over the dormant red algae, it wakes up and blooms. And when it blooms, it eats up all the oxygen so that the school of fish asphyxiate, and it creates an anoxic zone. They fall to the bottom and provide food for the red algae, and the red algae eats it. And when the ocean temperatures go up, we wind up with more of this stuff happening. And so the biosphere gets kicked in the pants by this red algae adapting to the conditions. So you can see how life works. These are conditions that we're starting to create. So you wind up with anoxic zones, sulfur dioxide, hydrogen sulfides, pestilence, cats chasing dogs, et cetera, et cetera.
Richard,
Yes,
is that red tide? Is that what
you have to stand up, Kara.
tide that we out? Or similar to
Yep. Kara's asking the question, is the anoxic zones similar to the red tide? And that's it, bingo. She's been doing her homework. I knew she'd try to trip me up. Oh yeah, she was a plant. So in addition to that, because of on the previous slide, we saw that the map showed that all the continents were all bunched together and there was very little coastline. And so the interior was highly desertified. It was there wasn't much water there. There weren't many lakes, and you had very, very dry conditions, and it became harder for life to live. And this particular extinction created an advantage for the dinosaurs because it killed off the mammal-like reptiles, it killed off the amphibians, it killed off a lot of creatures that would have competed with the dinosaurs and led directly to the age of dinosaurs. And so the dinosaurs were very happy about this. So maybe whatever supersedes us is going to be very happy. The end of the Devonian extinction, again, as we move further back into the past, less and less information available that is salient in terms of climate. So you can see here the positioning of the continents is now, this is before they come in to form Pangaea, but they're still sort of conglomerated, but there's a lot more coastline. The predominant life is in the oceans. So what we're looking at are fish life, fish-related life. They're the dominant top of the chain complex life form. It's really difficult to establish what's going on. Life on the Earth was becoming complex, but the biosphere on the Earth, or the pedosphere, wasn't as complex, nearly as complex as it is on the ocean. So you didn't have a lot of creatures running around, but they were there, mostly arthropods. So you had things like scorpions and spiders and centipedes and millipedes, that kind of thing. This particular extinction may have been due to anoxia related to weathering. So there was a lot of going on as far as plate tectonics was concerned. That means that there's uplift. With uplift, there is increased rainfall in certain areas, increased sedimentation, and that has an uptick of carbon dioxide, which leads to a global cooling. And so we're not certain what happened, but a surprising theory has come out that the Devonian extinction may have been due to a supernova that was passing by us. And it came in relatively closely. And this permitted a massive amount of UV to irradiate the Earth. It's not quite a fringe theory, but it's out there. Detecting a high mass neutron star or black hole after so many millions of years is problematic at this stage. They're hard to see. And the only way of detecting them is maybe through gravitational lenses. So this is the one that I'm interested in, because this is one that's similar to us. This is the end of the Ordovician. This is where we have sponges and trilobites and squid-like animals with shells, nautiluses, virtually no life on the Earth, on the continent. It's restricted to just a few mosses, not Duncan Moss, but my friend who's just come in. Bad pun, but I'm entitled. So mainly mosses, ferns, plants creeping out, maybe some beginning arthropods, that kind of thing. There was glaciation happening. This was icehouse Earth, and that relates directly to us. So if we can get similarities, the volcanism may have released aerosols into the stratosphere in the same fashion that the asteroid striking the Earth. So we have different mechanisms for achieving the same result. So with volcanism comes the blocking out of the sun if it gets into the stratosphere and it stays there for a while. So you wind up with an ice age. And also there was an indication that there was a lowering of the CO2 below a certain threshold. So that may also have led to the creation of ice at that time, but it's so uncertain because it's such a long time ago. So we're going to move back. So those are the 5 major extinctions, and those are the extinctions that are mass extinctions that are catastrophic, and we're trying to pick up bits and pieces from to relate to the climate crisis. And so now we're in icehouse Earth. Okay, so we're talking about the Cenozoic. So that is, it consists of the Paleocene, Eocene, Miocene, Oligocene, Pliocene, and the Pleistocene. And the last 3.5 million years have been the Pleistocene, in which we've had the heaviest glaciation. And some 35 million years ago, we started to get a cooling. After Petma, stayed warm for quite a long time for a variety of reasons, and then the temperature started to fall. And we started to see where the shifting of the continents, India moved very rapidly into Asia, and India collided with Asia, and that's the Himalayan mountains. And Antarctica broke away from India and went down to take its place over the southern pole. And it appears that that positioning of the continents, as well as the Milankovitch cycles, and we'll get into that in a second, cut us off from warm water circulation, and we started to get into icehouse Earth, where everything is cooled down. And so we wound up with newer ocean currents that changed the temperature transmission. Remember, 90% of the heat goes into the ocean. So how the oceans move is really important. How they transmit heat from one place to another, where the currents go. We get 25% of our total heat budget in the Maritimes from the Gulf Stream. The weather's affected by it. It doesn't feel like it today, but it is affecting us. So these newer ocean currents during the middle part of the Eocene actually contributed to the changing of our profiles and pushing us into what is now icehouse. And then there's also the weathering of sediment, again, because India is pushing up into Asia. You're pushing up the Himalayan mountains. And you've also got the crustal plates of the Pacific, the Nazca plate pushing into the South American plate, which has created the second highest and the longest chain of mountains, the Andes. And in part, the Rocky Mountains. But the Andes are much more significant in terms of their effect on the climate. And you can see that in the Atacama Desert, where it receives no rainfall at all. In some parts, they haven't had rainfall in 300 years. So these mountains go way up there, and they wind up with ice and weathering and water flow and all that kind of stuff. And this icehouse Earth started 35 million years ago. But what we're really concerned about is more recent. And we go from the Eocene to the Miocene. And this is where you wind up with the giant mammals. The Uintatherium, which is 20 feet tall and weighs 10, 12 tons, giant mammals, which lived at that time. And then things start to cool off, and you wind up with a change in the flora and the fauna, and certain animals being isolated from other animals and evolving in different ways. So Now we're going to talk about the last 2.5 million to 3.5 million years ago, the Pleistocene, which means the newest epoch. And we've been in ice age now for about 2.5 million years, not billion, million, sorry. In that time, there have been 11 major advances and retreats. In total, maybe 17 or 18, including the minor ones. And that means the ice advances, that takes anywhere from 40 to 100,000 years, and then retreats. And that takes about 10 or 15,000 years. And we hit the coldest point when the ice started to retreat about 11,000 years ago. And had it not been for people in carbon dioxide and methane and all that kind of methane and all those other greenhouse gases, we would have been seeing an end to this interglacial warm period, and we gradually start to fall back down into a cooling period. Well, that's not happening. You can see that we hit the peak, and had it not been for us, that would have been the end of it. And it got quite cold the last time around. We were able to survive it. There were humanoids for that whole period of time. It goes back almost 2 million years now, and we were able to survive it. The causes of this, we now know that a lot of the icehouse Earth at this particular time was caused by the Milankovitch cycle. Milan Milankovitch was a Serbian geophysicist who was looking at the influx of solar radiation into the Earth based on its tilt and its wobble and its orbit and its obliqueness of the orbit around the sun. And it goes in cycles, in 26,000 and 40,000 year cycles, and I think there's some shorter ones as well. Anyway, they're the predominant cause for our current icehouse. And this is what Antarctica looks like right now, and this is a direct result of the Milankovitch cycles. This also affects the CO2. With a lot of ice, covering the polar regions, and the greatest extent of ice is in the North Pole, not the Antarctic. The Antarctic isn't covering oceans, there's no life there. But what's being covered up in the Arctic Ocean is photosynthesis. And so none of that is happening. So the carbon dioxide feedback is starting to fall. And we know it's not the sole reason, and we're still trying to analyze why we're in this ice age cycle. But we know the Milankovitch cycles play a dominant role in it. So this relates to current tipping points. And what we see from the fossil record and the historic record is that there are the same themes coming up over and over and over again. And we call them tipping points. And this was coined back in the 90s. I'm trying to think of, there's a book. Of course, there's a book. Pardon me? Yes. Yeah, he coined the phrase. Thank you, Kara. Kara helped me out remembering that it was Malcolm Gladwell. That $20 is well invested. Anyway, Malcolm Gladwell came up with the term tipping points, and these are switches. So there are multiple tipping points. One is the two gases I've been talking about, CO2 and methane. The depletion of photosynthesis by microfauna that eats the CO2. Deforestation reduces carbon sinks. And so when you get a depletion of the microfauna in CO2, the temperature goes up. But the anaerobes make up for it as well. So this relationship is really complex as to how these various tipping points relate to each other, and which is dominant, we're not certain yet. Deforestation reduces the carbon sinks. We know that. We've seen that from the fossil past. Changes in polar albedos changes the amount of heat absorbed. So when we go from ice to water, that's a substantial change in albedo. It depends on how much is being reflected, not reflected. So when you examine tipping points, it's important to be able to relate those to species extinction. And when we see what's happening right now, these are the big things that come out. Methane clathates are something that come up over and over again, and the tundra emissions, the emissions that happen from methane bubbling up in lakes and in the great tundra, where the I guess the peat bogs start to melt and they release the methane. And then there's changes in the ocean conveyor due to freshwater ice melt, which covers it up, and you wind up with all kinds of changes in the heat budgeting of the Earth. What gets from the equator to the polar regions becomes a very important consideration. So these are the current tipping points that we can get from the various extinctions. And that's why we spent all this time looking at the chemistry, the physics, and then looking at the timeline of how the application of the chemistry and physics and the biosphere and pedosphere affect the climate. And so the next lecture, boy, I'm 2 minutes early. The next lecture, a couple of lectures, will be about the climate crisis big picture. Now that we know that it's related, that it's not just correlated, that it's cause and effect. And we're 99.9% certain that it is cause and effect. Now we can start to look at the big responses. And some of the big responses are this. Are they doing this? I like this, but I have a gut feeling that it's too little too late, and that we need more than just studies that are going on in the ocean, that we need immediate resolution. So what we're going to examine now, next week, is the big picture response. Money, large companies, governments from all levels, and what they're doing and what they're not doing, and how that works on the various tipping points that we've been talking about. So thank you very much. And any questions? I didn't see anything popping up from the internetosphere.
Yeah, there are two questions.
Oh, there are two questions.
Yes.
Oh, my goodness.
As soon as we get up here. I found the discussion of extinctions rather confusing. Some seem to be in chronological order, then reverse order.
Mhm.
Did dinosaurs disappear at the end of the Jurassic or the KT, or does the KT equal the end of the Jurassic? Could you please clarify?
Okay. So the clarification on the various extinctions, the big five are the KT, which ended the dinosaurs 65 million years ago, the Triassic, Jurassic 200 million years ago, during the age of dinosaurs, then the Devonian extinction 340 million years ago, age of fishes, then before that is the Permian 251 million years ago, the Great Dying, which ended the age of amphibians and ushered in the age of dinosaurs. And then we get to the Devonian 340 million years ago. And then finally, the Ordovician 440 million years ago. When I talked about them as an overview, I started with, can't remember, I guess it was the most recent, I started the whole lecture with the oldest and went to the newest. And then when I started talking about extinctions, I reversed that order. So I'm sorry that was confusing. So I hope that answers it.
Okay, one more. Despite Milankovitch cycles, is the sun still not shining? So why do global temperatures change, not just regional changes as Earth wobbles?
Oh, okay. So it has to do with the length of time various parts of the Earth receive heat. And most of the continental masses are in the northern hemisphere. And so with the obliqueness of the Earth changing and its elliptical orbit and its wobbling, where the sun is absorbed changes. And in the northern hemisphere, during the ice ages, we've had a lot of ice in the north. So the tilt towards the sun, we're actually further away from the sun in the summertime than we are in the winter as far as the northern hemisphere is concerned, changes the way that the sunlight is absorbed. So this is really important because of the variation of the Earth's surface and how sunlight is absorbed on the different parts of the Earth's surface when it's close or far away, pointing towards or pointing away. And it's quite a complex process. So I think the cycles are 26,000 and 40,000 years, and there's some smaller ones as well. So hope that helps. And that's it. Okay. Thank you.